Assalamu alaikum and good morning, everyone. Welcome to our session for Econometrics. And in this session, I will explain to you Chapter 2, the basic ideas of linear regression. So, regression in general plays a huge role in the study of economic analysis as it is used as a popular method to analyze the relationship between variables or to understand the econometrics or economics phenomena. It is very important to understand or to know that even though regression analysis deals with the relationship between variables or between a dependent variable and one or more independent variables, it does not necessarily imply causation, since causality must be justified or inferred from the theory that underlies the phenomenon that is tested empirically. So the regression analysis may have one of the following objectives. First is to estimate the mean or average value of the dependent variable given the values of the independent variables. We may have one independent variable which we can refer to as a simple regression analysis, or we can also have more than one independent variables, which we can refer to as the multiple regression analysis. Bear in mind that apart from using the term dependent variable, we can also use the term explained variable. Means that they are referring to the same thing. They are referring to the same concept. While on the other hand, independent variables can also be referred to as the explanatory variables. Explanatory variables. So, regression analysis, as I mentioned before, have one of the following objectives. First is to estimate the mean value of the dependent variable given the values of the independent variables. Second is to test the hypothesis about the nature of the dependence. Means that we may be interested to find or to identify what is the strength of the relationship between the dependent and the independent variables. Or we may also want to know what is the direction of the relationship between the variables. The variables may have positive relationship, or they may have negative or inverse relationship. We may want to know whether the independent variables are significant or not in explaining the movement of the dependent variable. The third objective of regression analysis is, of course, to predict or forecast the mean value of the dependent variable given the values of the independent variables beyond the sample range. Even though we may rely on the data that we obtain from a sample, but we may use the regression analysis to make some forecasts in terms of the movement of the dependent variable in its mean, given the values of the independent variable. And this is usually done in the finance industry, as well as in the other related fields of economics, in trying to predict the movement of the dependent variable given the value of the independent variables. In the policy making, this is also very beneficial in order to predict the impact of economic policies. Of course, the regression analysis can also be used to reach more than one objective. In other words, one or more of the preceding objectives combined are also the objectives of the regression analysis. You may conduct regression analysis in order to reach more than one objective in your study. As an example, suppose that we are interested in finding out whether a student's family income is related to how well students score on the mathematics section of the SAT test. So we assume that the mathematics SAT score is the dependent variable, while the annual family income is treated as the independent variable. The income variable has been broken into 10 classes. The first class represents the income of less than $10,000. The second group of income represent the income between 10,000 to 20,000, and we continue this groups until group number 10, where the incomes are more than 100,000. So for simplicity, we may use the midpoints of each of the classes. And from that, we set the midpoint for the first group as 5,000, as this is the midpoint for the first group, where the income is less than $10,000, while the midpoint for the second group is $15,000, as it is in between the income of 10,000 to 20,000. And we continue this approach for the third class, fourth, fifth, until class number 10, where the midpoint for class number 10 is 150,000. So assume that we have a hypothetical population of 100 students in high schools where there are 10 students grouped into 10 classes. So in total, we have a population of 100 high school students. From this table that you can see on this slide, this table can be interpreted as follows. For an annual family income of 5,000, one student scored a 460 in his or her math SAT test, while 9 other students also had similar family incomes, and their scores, together with the first student, averaged to 452, means that they are grouped in the same group of income where the midpoint is 5,000 and the average SAT score for mathematics for this group of students is 452. Here we have the second group of income. The first student in this group scored an SAT score or an SAT exam of 480. The second student that belonged to this same group scored 510, and on average, the SAT score for this second group of student is 475. And we can use the same explanation for the third until group number 10, where for group number 10, the average SAT score for mathematics section is 552. So the scattergram of the previous data is as shown here in figure 2.1. So in this graph, the horizontal axis represent the annual family income, while the vertical axis represent the student's math SAT score. Of course, for each income level, there are several SAT scores since we have 10 students per income level, 10 students per group of income level as shown here. We will have 10 scores plotted under each income category. In this figure, we have this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 points recording 10 average score, one for each group of income. So these points, as I mentioned before, this represent the mean values of score for each income level or for each income group. And as you can see here, it seems like there is an upward trend in the math scores, meaning that a higher income level tend to be associated with a higher math scores. And this is especially evident when the circles are connected. So these connected circles can be formally called the conditional mean or the conditional expected values. I repeat, these connected circles, these circles that are connected, they are called the conditional mean or conditional expected values. And the lines connecting these conditional means are called the regression line. And since this data represent a population of high school students, thus this regression line can be called as the population regression line. And this population regression line gives the average or mean value of the dependent variable, which is the math SAT score corresponding to each value of the independent variable. In this case, the annual family income in the population as a whole. So the population regression line, or in short PRL, can also be expressed mathematically. And since the population regression line in figure 2.1 is linear, we can also express them in a linear mathematical functional form as in this equation 2.1, where the first component here is the mean value of the dependent variable represented by y, corresponding to or conditional upon a given value of x. X is the dependent variable. In our example, x represents the income level. So the subscript I here represent or refers to the I subpopulation. Since we have 10 group of income based on the example of the maths SAT score, we will then have 10 subpopulation representing 10 I's. So the regression of y on x can be defined simply as the mean of the distribution of y values which has the given x. In other words, the population regression line, or PRL, is a line that passes through the conditional means of y. So if we can refer back to the subpopulation, as I said before this, we have 10 subpopulation if we are referring to the example of the math SAT score. So when x is equal to 5,000, 5,000 represents the first group of income. If I can show this table to all of you again. So if x is equal to 5,000, then y is equal to 452. So this is represented in this equation. When x is equal to 5,000, y is equal to 452. Y represent the mean value of y, or the average value of the dependent variable, which is the math SAT score. Of course, in this equation, we have beta 1 and beta 2. Here it is represented by B1 and B2. So B1 and B2 here, or beta 1 and B2 here, uphold the parameters. Or they can also be called as the regression coefficient. B1 here is the intercept, while B2 is the slope. The slope here measures the rate of change in the mean value of y per unit changed in x. While B1 here is the conditional, or shows the mean value of y if x is equal to 0. In other words, it gives the average value of the math SAT score if the annual family income were 0. So this is as explained in our previous session last week. Of course, in the future, expression like as in equation 2.1 in its first component can also be simply written as EY. In other words, the mean value or the expected value of y given a particular value of x at a certain subpopulation of y is also be referred to as the expected value of y as a simplification, as they are referring to the same matter or the same phenomena. Let us look into the regression function in a more specific manner. By taking into account on the stochastic specification of the function itself. So for that, let us refer back to table 2.1 or table 2.1. We know, for example, that corresponding to x that is equal to 75,000, the average value of y, the average value of math SAT score is 528 points. But if we pick one student at random for this category of income, we know that the math SAT score for that student will not necessarily be equal to the mean value of 528. For example, student 1 SAT score for this group of income, 75,000, is 530 points, and it is different than 528 points, the average value of SAT score for this group of income. And let us take another example. Take the last student in this group. So here we can see that the SAT score for this student is 500, and it is way different than the average score of 528. So how do we explain the score of an individual student in the relation to income? In other words, how do we integrate this information in our regression function? Well, the best way we can say, or the best way that we can do, is to say that any individual math SAT score is equal to the average for that group plus or minus some quantity. So how do we integrate this statement in the equation? Well, it is actually pretty simple. In order to express that mathematically, we can introduce another component in the equation. And that component is called the stochastic term, or can also be referred to as the random or error term, the mu here as represented in equation 2.2. So since we introduced that term, this equation here is called the stochastic population regression function, or the statistical population regression function. And this equation in its right-hand side can be divided into two components. The right-hand side of this equation can be divided into two components. We have the systematic or deterministic component, b1 plus b2xi is the systematic or deterministic component, and the second component in this equation is the non-systematic or random or noise component, represented by the error term or mu I here. So the reason why we call this component as random is because the value cannot be controlled. So what is the nature of the stochastic error term or mu? Well, there are four nature of the stochastic error term. First is that the error term may represent the influence of those variables that are not explicitly included in the model. For example, in our math SAT scenario, it may well represent influences such as person's wealth and the area where he or she lives, and it may also represent other factors such as the high school GPA or the math course taken in schools. The second nature is that even if we included all the relevant variables that determine the math test score, Some intrinsic randomness in the match score is bound to occur that cannot be explained, no matter how hard we try, because it is simply a human behavior. So in other words, the mu or error term may reflect this inherent randomness in human behavior, which cannot be explained. The third nature is that the mu or error term may represent the errors of measurement. For example, the data on annual family income may be rounded, or the data on math scores may be suspect because in some communities, few students plan to attend college and therefore don't take the test. And last but not least, the nature of the stochastic term can be explained based on the principle of the Occam's razor. The Occam's razor, where it states that the regression model need to be kept as simple as possible until proved inadequate. This is because, in reality, it is very difficult, if not impossible, to take into account all factors that can explain the dependent variable. If we are referring to our example, it is very much impossible or difficult to take into account or to include all variables that can influence the math SAT score. Apart from that, if we include all possible variables in the model may be impossible or impractical to be used. Let us move to the sample regression function. In reality, we know that it is very difficult to observe or collect the data from the population entirely. So in that situation, we may have to refer to the sample data based on the sample collected. So here we have two tables representing random sample from the same table 2.1. So the question is, can we estimate the population regression function solely based on the sample collected? We know that if we have, say for example, two samples, we will be able to create two different sample regression lines as shown in figure 2.3. So which one of these regression line that represent the true population regression line? In reality, there's no way we can ensure that either of the two sample regression lines shown here represent the true population regression line. And to make it more complicated, if we have 10 different samples, then we will have 10 different regression lines, and all of these sample regression lines are not likely to be the same. They will likely to be different from one to another. So based on the sample regression line, we can create the sample regression function as indicated in this equation 2.3. So it is the sample counterpart of the equation 2.1 shown previously. So here we have y hat or y cap, which is the estimator. It is the estimator of the population conditional means, while B1 is the estimator for beta 1, and B2 is the estimator of beta 2. B1 is in lowercase, and same goes to B2 is in lowercase when we draw the equation for the sample regression function. If we include the stochastic term in equation 2.3, we will create the equation that we have here, where instead of including the mu to represent the error term, here we include the stochastic term by or represented by EI. So EI is the estimator of the random stochastic version of the population. And instead of using the term error term or the random term in the stochastic version of the sample regression function, we call this term as the residual or the residual term. I repeat, when we refer to the stochastic version of the population regression function, we use the term error term, while in the stochastic version of the sample regression function, we use the term residual. So instead of using mu, here we are using E. So the residual here represents the difference between the actual values of the dependent variable, or y, and their estimated value from the sample regression. So we need to keep in mind that we are not actually, based on the sample regression function, we are not actually observing the beta 1, beta 2, as well as the error term. What we observe in the sample regression functions are the proxies of beta 1, beta 2, and the error term. Namely, we are observing the B1, B2, and the sampling error or residual. But similarly, we can also call B1 or consider B1 and B2 as the coefficient values. And these coefficients are proxies to the parameter values of beta 1 and beta 2 in the population regression function. So here we have a figure which indicates the population line or population regression line and the sample regression line. And we are aware that there is a difference between the population regression line and the sample regression line. So what we're going to do in this chapter is to find a procedure or a method to make this sample regression function as close as possible to the population regression function. As I said before this, it may be difficult, if not impossible, to collect the information from the population as a whole. For that, it may be very difficult or impossible to draw or to construct the population regression line and the population regression function. So we have to rely on the sample collected from the population. And from the sample collected, we can draw the sample regression line. And from the sample regression line, we create the sample regression function. So our job in the regression analysis is to find a way or to follow a procedure that will make the sample regression function as an approximation that is close to the population regression function, the close as possible or as close as possible. So it is fascinating to consider that this method or this approach can be done even though we never actually determine the population regression function. Even though we may not be able to know that the population regression, we may not be able to know the actual population regression function, but we can follow a method that will estimate the sample regression function that is close as possible to the unknown population regression function. The population regression function as well as the sample regression function that I've shown before are linear in their forms. And when we say linear, it can actually be interpreted in two different ways. One is the linearity in the variable, and this is perhaps the more natural meaning of linearity, which is the conditional mean value of the dependent variable is a linear function of the independent variables, such as we can see in these two equations, equation 2.8 and in equation 2.9. In equation 2.8, the independent variable or x appear with the power of 2, while in equation 2.9, it appears in the inverse form. Here we have 1 over x. X is the independent variable. And when we translate these two equations or functional forms in the form of a figure, we will be able to create a figure that is non-linear, as in figure 2.5b. So in 2.5b, we constructed the non-linear demand curve by following the equation 2.9. So this is the same as in equation 2.9, where y is equal to beta 1 plus beta 2 times 1 over the independent variable, or 1 over x, while the figure 2.5 is the regular linear demand curve. So this is as in population regression function that we have discussed before. So in the linear demand curve, or in the linear functional form, the slope for B2 is the same at each point on the curve. So the value of the slope, or the value of beta 2, remain the same across all values of the independent variable, across all price level, since x here represent price as we are referring to the demand curve. Of course, here we still have an inverse relationship between the variables, a negative relationship between the quantity demanded and the price value for the product. But in figure 2.5b, the relationship is non-linear. So the slope, or the value for B2, varies from point to point on the curve. The value for beta 2 are different depending on, or across different value of the price level or different x value. Another interpretation of linearity is the linearity in the parameter or the beta values. So it refers to the scenario where the conditional mean of the dependent variable is a linear function of the parameters. So it means that the beta appear with a power of 1 only. So it may or may not be linear in the variables. So if we are using this definition, then it means that both equations here, 2.8 and 2.9, are linear, while equation 2.10, on the other hand, represent the non-linear or non-linear in the parameter model, as here we see that the beta appear with a power of 2. So, of course, in our discussion, we are primarily concerned with the models that are linear in the parameter. So, in other words, from now on, when we say linear regression, it actually refers to a scenario where the mean of a regression that is linear in parameters, where the beta values are raised to the power of 1 only, and it may or may not be linear in the explanatory variables. Of course, the regression or the functional forms that we have discussed before this are referring to the simple regression only. As I said before, in the simple regression model, we have only one independent variable. But in a multiple regression model, a multiple regression model is a case where the dependent variable is a function of more than one explanatory variable, as shown in equation 2.11. So here, instead of simply having x2i as before, now we have additional explanatory variables represented by x3 and x4. Of course, here we have the expected value of y, which is the same or can be interpreted as the expected value of y given a particular value of three independent variables, x2, x3, and x4. And when we include the stochastic term, or when we include the error term, then we will be able to construct the stochastic specification of the model as in equation 2.12, where here we have the dependent variable y is explained by beta 1, which is the intercept, beta 2 x2, beta 3 x3, beta 4 x4, plus the error term. So here we have beta 2, which is the parameter for dependent or independent variable. 2, beta 3 is the parameter or the coefficient value for x3, while b4 is the parameter or the coefficient value for x4. Of course, when we say the stochastic specification or the stochastic model, we can also divide them into or differentiate them into two different components. Yeah. So component is the first component is the systematic or uh, deterministic component. And the deterministic component in this equation are the beta 1 plus beta 2x2 plus beta 3x3 plus beta 4x4. While the second component is the non-systematic or noise component, which is referred to the error term here. We know that we have to estimate the population regression function, or PRF, on the basis of sample regression function, or SRF, since in practice we only have a sample or perhaps two from a given population. So how then do we estimate the population regression function? Well, the most frequently used method is the least square, or popularly known as the method of ordinary least squares, or OLS. So how do we construct this least square method? We actually construct it by following the least square principle. Recall that based on the simple population regression function as shown here, the dependent variable y is equal to the beta 1 plus beta 2xi plus the error term value, or mu I. And since the population regression function is not directly observable, we estimate that population regression function from the sample regression function. So here we have the dependent variable yi that is equal to b1 plus b2x1 plus the residual ei. So b1 is an estimate of the parameter beta 1, while b2 is the estimate of the parameter beta 2. The residual component of this sample regression function can be written as ei, that is equal to the actual dependent variable yi minus the predicted dependent variable yi. Thus, the residual ei is equal to yi minus y hat I. That is also equal to yi minus b1 minus b2xi. So here we are using the equation 2.3. So the best way to estimate the population regression function is to choose b1 and b2, which are the estimators of beta 1 and beta 2, in such a way that the residuals, or ei, or which can also refer as the residual sum of square, RSS, as small as possible. So the least squares principle states that to minimize the residuals, the residual sum of square need to be equal to the sum of square of the difference between the actual yi with the predicted y. I repeat, based on the least square principles, the residuals, the E term, is minimized when the residual sum of squared here is equal to the sum of squared differences between the actual y with the predicted y. And it is also equal to the sum of squared between the actual y minus b1 minus b2 xi. So this is referred as equation 2.13. So how do we actually determine these values? To be more specific, how do we determine b1 and b2 here? Well, in order to do that, we obtain the following solutions for b1 and b2 by following the equations in 2.16 and 2.17. So here we have b1 is equal to y bar minus b2x bar. And the sample intercept is thus the sample mean value of y minus the estimated slope times the sample mean of x. So here we have b2, which is equal to the sum of xi yi over sum of xi squared. So what are these small letters refers to? Well, these small letters denote the deviation from the sample mean values, where the small letter for xi is equal to the xi minus x bar, and the small letter yi is equal to the yi minus y bar. So xi here refers to a specific or particular sample values at a particular observation, while x bar here refers to the mean value of the sample, the average value from the sample. And same goes, here we have yi, which refers to the particular value of y at a specific observation I, while y bar here refers to the values or the mean values of the dependent variable from the sample retrieved. And there are a number of interesting features of the ordinary least square. First one is this sample regression function obtained by the method of OLS, ordinary least square, passes through the sample mean values of x and y. So here the mean values of the dependent variable retrieved from the sample is equal to b1 plus b2 x bar. X bar here, as I said before this, represent the mean value of x from the sample. Apart from that, the mean value of the residuals, the mean value of the residual is always 0. So the residual, the total value of the residual divided by the number of observation in the sample is always equal to 0. And here, the sum of the product of the residuals and the value of the explanatory variable is also 0. So the sum of residual times the value of the independent variable is always equal to 0 as well, according to the OLS. And the sum of the product of the residual and the estimated dependent variable is also equal to 0. Means that apart from the sum of residual times x value is equal to 0 based on OLS, the sum of y value times the residual is also equal to 0. So those are some of the interesting features of the ordinary least squares. To make it more clear, here we have table 2.4. So this table 2.4 is retrieved from table 2.2 that we have discussed before this, and it refers to the math SAT scores based on the sample from that same population of math SAT scores. Here we have the value of the dependent variable based on the sample. 410, 420, 440, 490 down to 590. So we have a sample of 10 observation retrieved from 10 students from that particular population of 100. So here, the sum of SAT score for the 10 students in the sample is 5,070 points. So 410 plus 420 plus 440 plus 490 down to 590 is equal to 5070. And of course, corresponding to each value of the SAT score, we have the corresponding value of the income category. So here we have the income category. The first group of income, or the first category of income, is 5,000, followed by 15,000, and then 25,000, and last but not least, we have 150,000. So as a whole, we have a sum of incomes that is equal to $560,000. So 5,000 plus 15,000 plus 25,000 down to 150,000, we have a sum of income that is equal to $560,000. Here on the third column, we have the sum of multiplication between the dependent variable or the SAT score with the independent variable, the group of income or the corresponding income level. For example, for the first observation, we multiply 410 points with $5,000 to get this particular value here, that is equal to 2,050,000. 2,050,000. So we repeat the same process in order to get the multiplication for the second, third, until the last observation. Of course, we have the sum of multiplication between the dependent and independent variable indicated here, and it is equal to 30,555,0000. On the fourth column, we have the squared income value, or the squared value of the dependent variable. Sorry, the squared value of the independent variable, the squared value of x at each particular observation of I. I here refers to the specific or particular value of observation. For example, the first observation is $5,000. So this squared value of x1, as it refers to the first observation, is 25,000,000. And we repeat the same process again for the second observation. So the squared income for the second observation, or x2 squared, is equal to 225,000,000. All that you have to do is to square each value of income for each observation. We repeat the same process for observation number 3, observation number 4, down to observation number 10. Of course, even though I say down, it refers to the later observation until the last observation. And here we have the sum of squared product of the independent variable. Here it indicates that the sum of squared value of the independent variable is 476,000,000,000. Here on the fifth column, we have the small letter x. So what is this small letter x? As been mentioned before, the small letter x here refers to or denote the deviation of the income level from the sample mean of the income. So how do we get this negative 51,000 here? Well, first, we need to identify the mean value of income. So here we have 56,000,000, and we divide the sum of income with the number of observation. We have 10 observation. So 560,000 over 10 is equal to 56,000, and it refers to dollars. So it's $56,000. So x, small letter x here, refers to the deviation of income from its mean value from the first observation until the last observation. So for example, here we have negative 51,000. It refers to 5,000 minus 56,000. So that is what we refer as the deviation from the value of each observation of the independent variable with its mean value. We repeat the same process again for the second observation. So $15,000 minus $56,000 is equal to negative 41,000. So this is the deviation of x from its mean value for the second observation. And we repeat it again for observation number 3 until the last observation. So here we have 94,000, since 150,000 minus 56,000 is equal to 94,000. So here you can see that the sum of deviation, or the total deviation of each value of x with its mean value is equal to 0. Means that negative 51,000 plus negative 41,000 plus negative 31,000 down to 94,000 is equal to 0. And of course, on the next column, we have the deviation of y with its mean value on each observation. So 410 minus its mean value of 507 is negative 97. So how do we get this 507? Well, all that we have to do is to divide the sum of y to the number of observation, which is 10. So 5070 over 10 is equal to 507 here. So 410 minus 507 is equal to negative 97. We repeat for the second observation. So 420 minus 507 is negative 87. We repeat it again for observation number 3. For observation 3, so 410 minus 507 is negative 67. So this negative 67 is the deviation. It's the deviation of the y on each observation with its mean value. So it refers to the small letter y. Of course, here, the sum of deviation of y with its mean value is also equal to 0. So negative 97 plus negative 87 plus negative 67 plus negative 17 plus 23, and until the last observation, 83, here we have 0. The sum of difference, or the sum of deviation of y from its mean value. On the next column, we have the squared deviation of x from its mean value. So how do we get this? All that we have to do is to multiply the deviation of x for every observation with its exact value, or to get the squared product of the deviation of x for each of its observation, or for each of the observation. For example, the squared value of negative 51,000 is equal to 2601,000,000. Or you can also multiply this negative 51,000 with negative 51,000 to obtain the exact same value. Repeat the same process again in order to get the squared value of deviation for x on the second observation. So here we have 168,1,000,000. How do we obtain this? All that we have to do is to find the squared value of negative 41,000. So the squared value of negative 31, or the squared product of negative 31,000, is 961,000,000. So we repeat the same process again for the later observation. And here we have the sum of squared value of x's, the small letter of x's. So here we have 1624,000,000,000. Means that 2601,000,000 plus 1681,000,000 down to this last observation here, 8836,000,000, which is a very large value. Of course, here we have a sum of 1624,000,000,000. And we can, on the next column, we have the squared y, the squared small letter y. which is the squared value of the deviation of y from its mean value on each observation. So here we have 9409. How do we get this? All that we have to do is to multiply negative 97 with its exact value. Negative 97 times negative 97 is equal to 9409. Or you can also get the squared product of the small letter y. So negative 97 squared is equal to 9409 or 9409. We get the squared value of negative 57, that is equal to 7,569, and we repeat the same process until the last observation, until observation number 10. And here we have the sum of squared deviation of y from its sample mean value, which is 36,610. And the next column here represent the multiplication between small letter x with y, with small letter y. In other words, this column here represent the multiplication of the deviation for the dependent variable with the independent variable. In order to get the first value or the first observational value, all that we have to do is to multiply negative 51,000 with negative 97. We will get 4947000 or 4,947,000. For the second observation, we have 3,567. We get that value by multiplying negative 41,000 with negative 87. We repeat the same process again until the last observation. So here we have the multiplication value between the deviation in x with the deviation for y. So 94,000 times 83 is equal to 7,802,000. Of course, 21,630,000 is the sum of multiplication of small letter x with small letter y. The sum of multiplication for the deviation in x with the deviation in y. Moving to the next column, here we have the y hat. Y hat is the estimated value. Yeah, y hat is the estimated or predicted value of the dependent variable. So how do we get the predicted value of y here? Well, in order to answer that question, we refer back to this same equation where we know that the predicted y is equal to b1 plus b2 xi. And we also know from equation 2.16 and 2.17 that b1 is equal to the mean value of y or mean y minus b2 x bar. So here x bar refers to the mean x. And we also know that b2 is equal to the sum of multiplication for x and y over sum of squared x. And it means that in order to know the predicted value for y, we need to estimate b1 and b2 first. So for that, we at first need to determine the B2, because from B2 then we'll be able to estimate B1, and from B1 we will be able to know the y cap or y hat. So B2, by following equation 2.17, B2 is equal to the sum of xi times yi. X and y are both in small letters, which represents the deviation for x and y from their means value, from their respective mean values, over sum of squared x. So here, from the table 2.4, we know that the sum of multiplication between y and x is equal to 2,163,000. So we put that value as the we put that same value as the numerator. And we also know that the sum of squared x, by referring to the same table, is equal to 1,624,000,000. So we put that same figure, in this case, we treat it as the denominator. And of course, when we divide the 2,163,000 with the 1,624,000,000, we'll be able to get 0.00133. So this is the value for B2. Of course, if we are referring to exact value, it will be much more than 0.00133. But here we are using 5 decimal points. Okay, by having the value for B2, now we can solve B1. We know that B1 is equal to the mean value of y plus B2 times mean value of x. Mean value for y is 507. We can refer here. Mean value for y is 507 plus 0.00133. So this is the same as what we have here. It is the value for B2 times 56,000. So 56,000 is the mean value for x. Based on the sample, it is 56,000. So solving this, we have 432. That 432 is our B1, the intercept based on the function. Thus, y cap is equal to 432.4138 if you're using the exact figure, plus 0.00133x. So I repeat here, based on this B1, we have 432. But of course, if we take into account on the decimal points, we have 432.4138. So to make it more accurate, you can either use 4 decimal points, or if you want, you can also use 5 decimal points. But for me personally, by having 4 decimal points is sufficient. So instead of having 0.00133, you can have 0.0013 instead. But of course, if you have a larger decimal points, then the more accurate it will be. Okay, since we know that y cap is equal to 432.4138 plus 0.00133x, we use this same formula. We use this formula in order to determine the exact or the specific value for y cap, which is the predicted value of y for each observations. Means that in order to get the predicted value of y for observation 1, all that we have to do is to add 432.4138 plus 0.00133 0.00133 times the specific value for x for observation 1, in this case 5,000. And if you're following that formula, you will be able to get around the same figure as we have here, 439.073. But of course, as I said before this, if you are using higher or longer decimal points or larger decimal points, then it will be much more closer to this. Because if you are using simply 2 decimal points, 3 decimal point, for example, then the figure that you will get for y cap, or the predicted y, is not going to be exactly the same, but it will be closer, or it will be relatively similar to 439.073. It will be different, but the difference is not going to be that large. So as I said before, if you are using higher decimal point, then the figure that you will get will be much closer to 439.073. You repeat the same process again in order to get the predicted value for y for the second observation. So 432.4138 plus 0.00133 x, in this case, instead of getting 5,000, it will be 15,000. And from that, you will be able to get 452.392. Repeat the same process again using the same formula, 432.4138 plus 0.00133 times, in this case, times 25,000. You will get the predicted value of y that's equal to 465.711, and you repeat the same process in order to get the predicted value for the fourth observation until the last observation. Here we have 632.193, and we will be able to get that if we add 432.4138 with this 0.00133 times 150,000. You will get 632.198, or pretty much the same figure as we have here. If we find this summation of this predicted value for y, you will get 5070. And here you can notice that this figure is almost the same as the figure that we obtained from our observation based on the sample. So 5070 as well. Okay, so after we obtain the predicted value for each observation and the sum of predicted value of y, or the predicted y represented by y cap here, the next process is to determine the residual. Remember, the residual is the difference. Yeah, the residual is the difference between the actual y, so this is the actual y, based on each observation. So for the first observation, the actual y is 410, with the predicted y for each observation. So for observation number 1, the predicted y is 439.073. How do we get the predicted y? By estimating b1 and b2 at first. So here we have the residual for the first observation, which is negative 29.0733. So how do we get that? All that we have to do is to subtract the actual y with the predicted y. Means that 410, if we're referring to the first observation, minus 439.073, you will get that negative 29.0733. You repeat the same process for the second observation in order to get its residuals. Remember, if you're referring to sample, we are using the term residual. If we're referring to the population, we use the term error term. And in the population, the error term is represented by the symbol mu, while in the sample, the residual is referring to the or represented by the symbol E. But they are pretty much the same in terms of concept. where they refer to the difference between the exact value of y with the predicted value of y. Okay, so here we have negative 32.3922. We obtain this by subtracting 15,000 with, sorry, not 15,000, 420 with 452.392. We repeat the same process in order to get the residual for observation 3 until observation 10. So here we have negative 32.1982, which we obtain by subtracting 590 with 632.198. So of course, as been mentioned before this, among the features of the OLS estimator is that the mean value of the residual is equal to 0. So here we have the sum of residual that is equal to 0 over the number of observations. We have 10 observations. In this particular sample, we obtain the mean value of residual that is equal to 0. Of course, 0 over 10 is equal to 0. Okay, we can proceed our estimation by identifying the squared residual. So the squared residual is simply the multiplication of the residual for every observations with its exact same value. For example, negative 29.0733 squared is equal to 845.255. We repeat the same process for the second observation. Here we have negative 32.3922 squared is equals 1049 or 1049.257. And we repeat the same process again until the last observation. Here we have the squared residual equals 1780.694. So the sum of squared residual is equals 7801.0776. On the last column for this table, we have the sum of product for the residual and the small letter x, which is the deviation of x from its mean values. So in order to get the multiplication or the product, all that we have to do is to multiply the residual with the small letter x for each observation. For example, by multiplying negative 51,000 with the residual negative 29, we will get the product, which is in this case is equal to 148,273.069. And we repeat the same process in order to get the product for the next observation. The product means the multiplication value of small letter x with the residual for each observation. So here, negative 41,000 times negative 32.3922, we obtain 1,328,081.897. We repeat the same process for observation number 3 until the last observation. So here for the last observation, we have 94,000 times negative 42.1982. We obtain negative 396 6637.931. Of course, when we get the sum of the products from the first until the last observation, we will be able to get a sum of 0. So here, of course, before I forget, so here we are using an example of 4 decimal points for beta 1, sorry, not beta 1, but B1, and for B2, we are using 5 decimal points. But I suggest that if you want to try on estimating the predicted value based on a sample, kindly use standardized or similar decimal points. If it's 4 decimal points for B1, then use similar 4 decimal points for B2. But here in this case, I made a mistake because 1 is using 4 decimal points for B1, while B2 is using 5 decimal points, which is inconsistent. Okay, so this, on the other hand, is the value obtained from the same sample value. So here we have the estimated value of y, or y hat, that is equal to 432.4138 plus 0.0013x. And we can draw a line or regression line based on this, what we call as regression. And that regression line is as indicated in figure 2.6. So here we have a regression line that is close to the population regression line. So this is the closest regression line to the population regression line. By using or by referring to the sample collected in that particular population. And of course, here it says that note that we have put a cap on y to remind us that it is an estimate of the true population corresponding to the given level of x. Okay, so they are not the actual they are not the actual estimation based on the population, but they are the estimator of the actual value of y obtained from a sample collected corresponding to the given level of x. So based on this value, what can we say, or how do we interpret this B2, which is in this case equal to 0.0013? Well, it means that, remember that this is the slope coefficient. It means that other things remaining the same, if annual family income goes up by $1, the mean or average math SAT score will goes up by about 0.0013 points. So that is what this B2 represents. While for the intercept here, 432.4138, it means that if family income is 0, then the mean math score, remember, the mean math score will be about 432.4138 points. But of course, it is very often that such an interpretation has no economic meaning. So it means that usually when we run regression or when we conduct regression analysis, our main focus is towards 0, towards the beta 2 only. But of course, if we can rephrase what this intercept means, we can also say that the intercept shows the mean or the average effect of y, or the average effect on y of all the variables, or if all the variables omitted from the regression line. I repeat, the intercept here shows the mean or the average effect on y if all the variables omitted from the regression analysis. So I guess that's all from me for this session. I hope that you understand the things or my explanation for this particular topic. And until we meet again on the next session, thank you very much.